Thanks to everyone. We're really excited to be here, and my husband just gave me a thumbs up, which either means my luggage arrived or you can't tell I smell badly. I'm not really sure. But I really want to thank Pierre. This has been lovely, and really appreciate all the work you've done making this a wonderful time for us. So I'm going to talk about something I haven't talked about before, so I'm a little nervous, but the good thing is I have all the experts in the room, and we're about to submit our paper, so we'll be really interested to hear what suggestions people have and comments people have about this problem, which is something that I've been thinking about with colleagues for quite some time. So I want to acknowledge them in case I forget later. The lion's share of a lot of this work has been done by Sally Paganin, who is about to receive her doctorate at University of Padua in collaboration with David Dunson and also Andy Olshan, who is an epidemiologist at the University of North Carolina at Chapel Hill. And so just by way of introduction, I'll tell you a little bit about clustering. So there are many experts on the topic in the room, but clustering is a common goal of data analysts. And in the study that I'll talk about, something that we're very interested in for a variety of reasons. There are two different schools, big schools of clustering, people who are using distance-based methods. Here we'll use, not necessarily have to specify a data generative model for the data. And then there are model-based clustering methods, which is more what many of us work with, relying on discrete mixture models. And so nice things about the model-based clustering perspective for the purposes of our talk today are that it lets us get information about the posterior distribution on the clusters, which is something of interest, as well as allowing us to incorporate prior information on the clustering, which is something else that's important in this problem. The applied problem that we are interested in is the study of birth defects of unknown etiology. And so in particular, what the investigators would like to do is look at a variety of exposures of interest. And these range from things that you can't really control, so your maternal age, race, genetics, things like that, to behavioral characteristics, medical or other biological characteristics. They want to know how those are related to the risk of a birth defect. And there is some prior information available, both on how some of these exposures may act in terms of affecting your risk, and also on how the birth defects themselves are related, and that's what we'll talk about today. And so we'll be talking about methods that facilitate clustering adaptive to the data using both information in the particular data set we have, and then also external knowledge informed by what we know about embryologic development. So just to give you a little bit of background on birth defects. Birth defects in developed countries are a leading cause of infant death and deaths among children aged 1 through 4. Okay, globally the picture is a little different, and we still unfortunately have large infant mortality due to things like infections, diarrheal disease, complications of childbirth. You may not realize that the prevalence of birth defects is around 1 in 33. Okay, so chances are somebody in the room was born with a birth defect that may or may not have been diagnosed. The cause of the majority of these birth defects is unknown, and the risk may involve complicated interactions among factors, which is one thing that makes this type of data very interesting to study. And I also like to think about gastroschisis is not a very pleasant defect. It's fortunately something that can be remedied with surgery. It's when part of your intestines on the outside of your body, but it's nice for someone of my age because your risk plummets as you get older and you gain weight. And so it's a very interesting defect. The highest risk people are very young mothers who are very skinny. The birth defects are really heterogeneous, and this is our son, so this is another reason we sort of got interested in the area. And Peter, for example, was born with a really rare defect, and he had to have surgery when he was an infant. And of course, even though we're kind of crazed at the time, we're trying to figure out something about the defect. We're looking through the literature, and we could only find 8 case reports in U.S. or English language journals of his particular defect. So it was an interesting case, both as parents, but also working on a birth defect study to see, does he even pop up? Because this is a defect that's incredibly rare. We may not ever be able to say anything, useful about the defect that he has. And so that was one reason we got very interested. You can see he's really doing just fine. So the study we have is an interesting study. It is sponsored by the U.S. Centers for Disease Control and Prevention. It's carried out in 10 states around the U.S. And the target for each of these states is to recruit 300 cases of a variety of types of defects and 100 controls every year. Okay, the cases have to be viable live births, and in some states they're able to get information about elective abortion. Sometimes there's termination due to the mother finding out, the parents finding out the baby has a defect that might not be survivable. The important thing to know about this study is that the defects are confirmed and classified by geneticists. So there's a whole team, for example, of cardiovascular geneticists who classify every single defect. So birth defects research can be really hard to do if we're just looking at records-based studies where they haven't gone in and clinically confirmed and classified every case specifically. So some of the types of analyses I'll present later would not be very meaningful if we didn't have a study where we'd gone in and for every single birth defects case done a very precise classification of the type of defect, because this can be kind of tricky when they're making an on-the-fly decision, you know, in the delivery room or something like that. The controls were identified using hospital records or in some cases birth certificates. The data collection is a little bit complicated in that birth defects are relatively rare. They're generally not studied prospectively, and so most of the time you're doing a retrospective study, and you can't call the parents, for example, when they're awaiting their son's surgery at 6 days old and expect to recruit them in the study. So there's a window of up to 2 years during which time the parents are called and asked a variety of questions on their exposures and behaviors during the pregnancy. So a little guide to some of the exposures we're interested in. The outcomes that have high enough prevalence to be included in the study are roughly 80 different types of birth defects. And even there we get small samples, and I can give you some examples, especially when we look at exposures we're interested in. So we're interested in things like demographics and biological variables, so paternal age, maternal age, weight, lifestyle factors like exercise, like diet, drug use, drinking, smoking, factors related to the pregnancy itself. A very interesting set of factors people are interested in are pharmaceutical exposures and their indications. And these can be really hard to tease out. So anti-epileptic drugs are known to be teratogens, but then epilepsy is also not a good thing untreated in the pregnancy. And so you might have looking at exposures to antidepressants, but also to depression as a medical condition and so forth. And then of particular interest to me have been some of the environmental and chemical exposures. And these are things that are measured either by questionnaires or sometimes coded through the parent's occupation. So for example, an artist might be an occupation you might think would be suspect because if you're an oil painter, for example, you have exposures to solvents and things like that that could be bad. So we'll focus today on heart defects because we know a good bit more about heart defects than we do about defects in other systems. And so they're relatively frequent in the land of birth defects. So you can see about 1 in 120 babies here in the US are born with some sort of heart malformation, but they're very diverse, okay, and this causes problems. If we look in this study, which now has something like 40,000 individuals, we still have fewer than 20 defects that really have any kind of reasonable power to look at if we're looking at the defect individually. And so often what people will do is group defects together. Okay, this is something that's very controversial, and so for example, it's generally believed by experts that if you look at all heart defects together and any heart defect, that's really worthless, okay, that the heart defects are too diverse to group in that big of a cluster together to analyze, and so people will then look at subgroupings, and we could, you know, subgroup them forever. The way they're classified and the classification we'll talk a little bit about today is a mechanistic classification that relies on knowledge of embryologic development, so when certain parts of the heart are forming. And then the other thing that's important to think about is that the classification is hierarchical, so you might have any birth defect, then a heart defect, and then heart defects in certain areas and so forth. And you could keep going down a tree into the leaves as far as you really would like. So in the study that we're looking at, which is, and we'll talk a little bit later about what I mean by big data, these aren't massive data, we run into problems with small cell counts, and the example is in occupation. And if we look at the occupations of the fathers, we had 8 fathers who were identified as artists as their occupation. All 8 dads had babies with birth defects. No artists had control babies in the study. So Now, I don't think we should tell our children, at least not for this reason, to avoid starving artists or any other type. It's a potential mate. However, what do you do? I had a student come to me. She was working on parental occupation and birth defects as her dissertation in epidemiology. And she wanted to know what type of estimate to report in her paper. Do you report an infinite odds ratio for exposure? Do you ignore the artist entirely? What's the answer to this question? And 2 of these defects, hypoplastic left heart syndrome, there were 2 babies without, and that's a really nasty one. So the survival rate to adulthood is just about 70%. So one of the poor prognosis defects. We don't really want to ignore the fact that that happened. On the other hand, you don't tell your daughters to avoid artists entirely. We don't necessarily believe that. So we got really interested, looking at an example like this, thinking about our son, is how you borrow information to get reasonable estimates so that we can say something maybe about some of these more rare defects, and defects that aren't particularly rare necessarily, but because we're looking at some interesting exposures, the sample size all of a sudden in certain cells starts to get small. So the lumping versus splitting challenge is what this is called in epidemiology. You see it a lot also in taxonomy. You see it in precision medicine, where they're trying to figure out how precise they want to get when they're recommending a treatment for you. And so I'll just spend a little bit of time thinking about that. In the birth defect setting, ideally any classification I would use reflects some sort of understanding of how the defect came about. Okay, and the process of both the process of the development of the organ and also what might cause something to go wrong in that process. And I could subclassify defects, infinitely based on their severity, based on where they are happening in the body, based on what we know about what might have caused them, based on when in development that birth defect occurred, and based on, for example, the prognosis to the child. So we could go on forever coming up with subclassifications of defects. But if we do this excessively, we'll have no power, okay? We'll lose precision. If we aggregate too much, if we look at all heart defects, then we may not be able to say much about them because we've just grouped apples and oranges and pomegranates and everything all together. And so the other challenge we have is, even if I have a very precise, even if I have some classification in birth defects research, it's not generally accepted by everyone. So there is some uncertainty associated with these mechanistic classifications of defects. So, one paper will use one classification, another paper will use a slightly different classification. So even if we've got something in this field, we don't really know that that's the best thing we should be using. So how should we be clustering these defects? So that's the basic problem, and now I want to talk a little bit about the methodology that Sally and that we have developed. And this is a very interesting, an interesting game. So this is one of Sally's slides from her presentation of her research for her thesis. And this game is a Japanese game from around the 1500s, and maybe others know more about it than I do. Jinjiko, is that close?
I actually have no idea.
Okay, see, he plays it all the time. So this is an incense-related game, and so you have 5 incense sticks, and you don't know which ones are being burned, and you're supposed to be able to identify, they're burning these 2 fragrances together, or so you're given a bunch of different scents to smell, and you're supposed to identify which combinations of scents you're being presented with. And this diagram that you see is showing all the different ways that we could take the 5 sticks, okay, and partition them. So if you look at the bottom, you're burning all 5 sticks together. The one above it, you're burning 3 together, and then 2 together, and then so forth. And so these are the different combinations that you might get. And so that's this, just an illustration of this set partition, of this collection of subsets. And so we'll be thinking about partitioning the set of different types of birth defects. Okay, so these 80, we won't be working with a full 80, but a variety of different heart defects. How can we cluster them? How can we group them in defects that might have common, groups of defects that may have common determinants or other similarities? So a couple of things that we'll be interested in when we think about these set partitions. The first is how many partitions we might have of, say, n defects into k blocks, okay? We'll be interested in the total number of set partitions, and then we'll be interested in the block sizes, so how many defects are in each block, okay? So we can think of B, the Roman letter, B representing the indices of the defects that are in a given partition. So useful for computation is to think about a Hasse diagram. So here now, just to make it all fit on one page, I've gone from thinking about 5 instance sticks to 4 dots. And if you look at the bottom 4 dots, this has all of my 4 items in a single cluster. And at the top, the colors to use, the 4 items are all in different clusters. Okay, and so this is just telling us now, this diagram tells us how these different sets and subsets are related to each other. A couple of things that are useful when we think about these partially ordered sets. The meet operator gives us the greatest lower bound of 2 sets. So if I think of 2 sets, and just because they're the 2 I can reach, we can think about these 2 black and gray ones on the left. Okay, so if we think about the largest subset of those, it's the set directly above. Okay, and then we can also think about, well, what's the lowest upper bound of 2 sets? And so if I take the 2 sets, then what's the smallest set that contains both of those? Well, that would be this one. Okay, and smallest meaning closest connected by 1 line on the Hasse diagram. And so this will be important when we think about doing posterior computation, so we'll come back to these ideas. So talking now about how we think about this clustering and how we build in uncertainty in our clustering, these set partitions are a key parameter in Bayesian mixture models, okay? And so the base assumption that we might make is that we have observations, and these are conditionally independent given a cluster assignment, okay? So we can think about theta being some parameters specific to cluster K, and then we can write our data model in the following format where we have some parameters theta we'll be estimating. In a fully Bayesian framework, we'll assign some prior distribution, okay, and then we'll be able to get to a posterior. One thing that gets really challenging is that very quickly, if we think about the number of set partitions, this grows really extremely quickly in the number of elements we're trying to deal with. So, you know, if we have Genji-ko, we have something like 52 set partitions, and if we have, instead of 5 items, 12 items, we're already in the millions. And so computation, dealing with, you know, thinking about visiting each one of these configurations is very difficult. So Bayesian nonparametric procedures typically build on discrete nonparametric priors that have a form such as this. So this is a general class of Gibbs-type priors. And these induce a latent partitioning of our data. And this partitioning depends on the number of clusters and the cluster sizes, okay? And we can think about the induced prior on the partitions or exchangeable partition probability function. And here you can see what it looks like for the Dirichlet and Pitman-Yor processes, okay? And so here we see these are just depending, once we marginalize out of the other variables, on how many elements here, for example, in the DP are in the partition, so the cluster size. Now, other types of methods we might use in this setting, we might think about the literature on covariate dependent clusters. So we might have features X that are available for our observations that help us in clustering. So there have been a lot of people in this room who've worked on this problem. So Peter has some nice papers, Antonio and Igor, I don't know if Igor's here yet. Antonio and Igor, David's worked in this area. Different ways to try to allow the clustering to depend on covariates, to allow exchangeability to be relaxed a little bit and consider exchangeability within groups and so forth. So these are some methods out here. Our context is a little different because what we have, and we think about the clustering that we've been provided, that we found in the literature, as a prior guess of the partition, okay? And so one thing that an epidemiologist might do is, instead of looking at all hard defects, they might look at defining 6 or 8 groups, and some might be the septal defects, and another group might be a different type of a truncal defects, and so forth. But they're uneasy about that classification because they're uneasy a little bit as, they have some uncertainty in that being the right way to break these defects up into groups. But they're confident enough that they think it's not bad, right? They write a paper, they propose this clustering algorithm, gets published in a good journal, but they recognize that that's not the be-all and end-all, and depending on what your inference is that you're trying to make, it may or may not be the right type of clustering structure to use. So how do we use knowledge like we have, which is a prior guess at the clustering? Or how do you incorporate other types of information? Things like how many clusters you think there should be. So I run into this problem a lot when I try to use clustering in epidemiology, because the clustering algorithms I'm often using are greedy and they want to fit the data better and better, and I get more and more and more clusters. I'm sure we've all been there. But the epidemiologists, really don't want to tolerate more than 4. Okay, and they want you to find 4 patterns, and unless one is really interesting and it's number 6. So it's a little flaky, right, how to do that. So maybe we have prior knowledge about the total number, the maximum number of clusters that might be tolerable or something like that, or about what size we want the clusters to be. So in epidemiology, they often have this ad hoc criterion to keep the number of clusters from growing too much, saying, well, once we start getting clusters that are less than X% of the data, we're not going to count those as clusters anymore. Okay, so they'll chop off the small ones. So the idea that we're working on is to propose a general strategy to modify an EPPF in order to not really center maybe, but focus the prior distribution on a specific partition, okay, that's specified in advance. Okay, and so we're going to call this partition C0. Okay, and so this C0 is going to be the grouping of my birth defects into a variety of different groups that are informed by the literature. And was this work, or sometimes I do really poorly with these because I'm not very calm. Just be sure, okay, well, that's all right. So we have a baseline distribution, exchangeable probability function, it's P0 of C, and then we're going to modify it, okay, by a suitable distance between partitions. Okay, and we'll talk a little bit about how we pick this distance. So distance between any given partition C and our base partition C0, baseline partition. And so we'll think about what kind of distance metrics make sense there. And then we'll also think about a penalization parameter, C, that's going to control the centering, okay? So, so for C is 0, we're just going to be collapsing back on whatever our baseline distribution is. And as C gets really, really, really large, then we're going to force basically everything to fall into the clustering we pre-specified in advance, okay? And so this will be a modifiable parameter. And so the last thing I want to talk a little bit about are sets of partitions with a given distance from C0 and a given configuration, okay? And so we'll be talking about that in terms of S. So here we have these distances that are almost surely discrete, and so we'll think about distance delta L, okay, where we're looking at, the closest partitions, the next closest partitions, and so forth, and that'll be of interest again as we think about posterior computation. So the analytic form of our process is as follows. So you can see it has sort of a familiar look. If we pick, for example, as a baseline the uniform, then G of lambda C is just 1. Also has a fairly simple form for the Dirichlet process. But we can use this. It's pretty easy to do computation, not that tricky if we're using some sort of Monte Carlo method. So the posterior computation, the way it looks depends on how we pick this baseline distribution. So if we have Gibbs-type priors, we can rely on a Polya-Orn representation and use some type of marginal sampler. Okay, if we're using a uniform as our P0, then we can use a Metropolis-Hastings algorithm. So computation isn't really too bad for these. But an important consideration is how we pick the distance, okay? And so what we're doing for our example, what we felt like made sense is using the variation of information, which is just a modification of mutual information so that it's an actual distance. And so it has a form given here, and you can see it actually has a nice interpretation and heuristic in that h of c is going to represent the uncertainty in the cluster allocation of a randomly chosen unknown data point given a particular clustering of the data points, okay? And h of c, c prime, this is going to represent the reduction in uncertainty of the allocation of a data point in C when I know where that data point would have been allocated in C prime. Okay, so that's telling us about sort of the mutual information there in that data. And so the distance for a given prior partition is going to take on a finite number of discrete values, and we'll be thinking about sets of partitions that are a given distance away. So the closest partitions to the base one, the next closest set of partitions, and so forth as we do our posterior computation. So just to give you a little bit of an idea about how this, what this looks like, if we think about the induced prior structure, here are what we've been given by the epidemiologist, for example, is sort of like an all hearts classification. Everything's all together in one cluster. Okay, on the left you can see, these are different blocks. So we have 5 objects that we're trying to cluster, and we have equal spacing going all the way up the y-axis, reflecting that this is a uniform, okay, where phi is 0. And then as our weight parameter, or c, sorry, as our weight parameter, I shouldn't have c and c, I could call it psi, but I had to take Greek in college, and I feel guilty doing that because they wouldn't tolerate that for some reason. So anyway, so the Greek C, right, as it gets larger, we're putting more and more weight, okay, on what I've specified a priori. And so this is a cumulative probability plot, okay, so that's why they're equidistant there on the left. On the right, you can see with a larger C, we're putting a lot more probability to start on this one block, okay? So that's the interpretation of that. You can see on the right now I have a different prior specified where I have 2 groups of 2 and 1 group of 1. And you see there on the left again, this is a uniform. So we have equal distance, so equal increments in the cumulative probability across the blocks to start. But then as my C parameter gets larger, right, on the prior I'm putting more and more mass on what I've specified based on the literature. And there's a jump in the middle of the 3-block range once I hit something close to this, okay? So it depends on, we don't have all the same prior probability for every configuration that involves 3 blocks, because maybe I have a configuration that's, you know, 5, 1, 2, 4, 3, that's pretty far away from this, as opposed to something that's 1, 2, 3, 5, 4 or something. So that gives you a little bit of intuition of how this works for the uniform. For a Dirichlet process where we have alpha equals 1, you can see it works a little bit differently. So, so based on how you might expect the Dirichlet process to behave. So now we don't have uniform probability. To start, we have C equals 0 is just going to collapse back on the Dirichlet process. So there we have a lot more mass on one cluster to start. And then you can see pretty quickly it likes just having one cluster. And then for the other configuration as well, you can get a little sense of the behavior. So how do we choose this parameter C? So this is something that actually took us a long time to think through. Okay, so we can evaluate the distribution of distances. And the thing to keep in mind is that the space is going to grow really quickly, okay? So here we have, 20-something heart defects, and so the space that we have to think about is exceedingly large. So we can't exactly list all our partitions. And so, that's something we need to think about. So how do we calibrate the prior? So one thing that we have done is thought about and we have sort of a hybrid method. So we'll do a deterministic search, a local search based on a Hasse diagram. And so we'll start in a neighborhood around the base prior, or the base configuration that we specified, so C0. So that's, you know, putting all the conotruncal defects together and all the septal defects together and so forth. And so what we'll do is we will explore in that neighborhood, okay, all the directed connections on the Hasse diagram. And so that's, so in that local search, this is sort of how that would work. So let's say my C0 has 1 isolated and then 2, 3, and 4 together. Okay, so that's in the top left in black. And then the closest partitions to that on the Hasse diagram are in the dark blue, and then the next closest are in the lighter blue, and then the furthest away are sort of grayed out there. And so that would be the order of exploration in the local neighborhood, okay? Now, what we'll do, however, to augment that is do a random sampling of partitions. Okay, so we'd like to get outside of that, we need to get outside that local neighborhood, we need to know how big it is, and so then we can randomly sample. Okay, so we can sample a number of blocks, and then conditional on the number of blocks, generate a partition. We can look at the distance, we can compare that distance to the maximum distance in my local neighborhood. Okay, and then we can use those accepted partitions to get estimates for distance values that are greater than that. So it gives us some idea of how big the space is that we're dealing with. And so here are just some, so one thing that we did in the paper is we just did some simulations to look at different base measures and try to think of, for example, you know, if we randomly sample from the prior distribution, what percentage of configurations would be within a given distance of our C0? Okay, and so so here this is constructed thinking about, say, getting X, you know, 90% with of the randomly sampled partitions would be within a given distance of C0, and that's how we're going to pick our C parameter. Okay. So how do we apply this to the birth defects data? So we have J indexing a variety of different heart defects, and then we have a number of babies in the study, which either are control babies or they have a specific type of heart defect. And then, oh, I'm using an old version of my slides here. Oh, that's too bad. So I have a flashy picture you won't see, and I apologize for that. We have some covariates associated with each defect here. And so those covariates will be separate for each baby, okay? And so what we're really interested in this, we're interested in 2 things in the study. The first is, you know, what's associated with the birth defect. So it's not really a study design where we can actually say at the end of the day what caused the birth defects, but we'd like to know what factors are associated with them. And so we're interested in a logistic model, for example, where I'm looking at the probability of having defect type J. And so these defects are really different with respect to their baseline prevalence, okay? And so we have a defect-specific intercept. And then what an epidemiologist might do is group all the conotruncal defects together, define a new outcome saying any type of conotruncal defect, and have a regression coefficient, a beta coefficient, you know, for that whole class of defects, okay? And X would be those with the predictors that might be related to those defects. So we'll look at that. The other thing we're interested in this application is, well, which grouping should we use, okay? So if not C0, is there something that's better? And so we're also interested in posterior inference on the clustering itself. So C0, again, is determined in this example based on a mechanistic classification of defects that's published in the literature. So as an epidemiologist, if you fit a group logistic regression, birth defects in the same group are all going to have the same set of coefficients. We'll have a defect-specific intercept because the prevalences vary widely, but then we'll have shared coefficients. And so we could model these in different ways. We could use, for example, which I've used in the past for this type of problems, we could use a Dirichlet process prior, but then we could also use a centered partition prior, okay? In order to do posterior estimation, we're just using polygamma data augmentation for the Bayesian logistic regression, introducing latent variables, and then we're using a class allocation step, okay, and then we're marginalizing out over the classes to get our beta coefficients. So what does this look like? So this is what happens, and I'll take a little time with a plot because the first time I looked at it, I wasn't really quite sure what it does. But if you look on the y-axis and the x-axis are the same except for the coloring. Okay, the colors in the abbreviations on the y-axis correspond to our C0. Okay, so if you look here, coarctation of the aorta and aortic stenosis, those are in pink. They were grouped by the embryologist into the same group as interrupted aortic arch type A, which is sort of in the middle, and hypoplastic left heart syndrome, which was the nasty defect that the two kids of the artist had, okay? And so that group had 4 heart defects in it a priori in C0, okay? Then the next one, pulmonary valve stenosis, is in light blue, and you can see 1, 2, 3, 4 light blue defects, so they were another group in C0. And then red, and then the dark blue, they're all sitting up there next to each other and so forth, okay? So the colors on the y-axis are telling you about what was going on in C0. This is a regular Dirichlet process prior, okay? So we're assuming exchangeability, and we haven't incorporated, in this case, our prior guess into the analysis. Now, if you look at dots, the dots along the diagonal are just to give you an idea of where C0 was in the 3 clusters that were determined. So the DP found 3 clusters. In the top right, you can see there are no dots there. That cluster is a subset of one of the original clusters in C0, okay? So it kept those 2 together. But then you can see the second cluster, which is not that large, had 2 elements, defects from the blue group, 1 red and 1 baby blue. And then the big, the big square in the middle is a little bit all over the map. It has all the green defects. They were all kept together, but some other defects were added into that grouping, okay? So it's a little hard to know what to do with this, especially when you go back to an epidemiologist who has some understanding maybe of the mechanistic classification, but then sees that you've come up with a group that looks a little different from what they may have expected, okay? So maybe they're really happy with the top right square, but they don't necessarily know what to make of this grouping all in the middle, okay, which is pretty agglomerative. So here are the corresponding results when we fit the model, and now for the sake of visualization, the ordering on the y-axis has been changed, okay? So you can't directly compare, but this is using a centered partition process, one with a C of 80, one with a C of 120, okay? And so this is placing different amounts of weight on our a priori partition. So if you go over here to the far right, you can see now, well, now I have, kept all the blue traits together, which was, which is nice. Most of the green traits are together, the pinks are all together. So you can see this is looking a little bit more like C0 than we had previously. If I have a more moderate value of C, of 80 here, you can see I've got a group, again, a lot of the blue defects are wanting to stick together, so there's a little more maybe agreement about that classification. The pinks are together again and so forth. So you can see these have been shrunk back towards our prior guess at what the structure might be in this analysis. Now, one thing that was of primary interest in the analysis is what these exposures do with respect to risk. And so here what we've done is we've taken 4 of the individual defects, so truncus arteriosus, partial anomalous pulmonary venous return, which is not a very nice one either, pulmonary atresia, and atrioventricular septal defect, which is not the best type of hole in the heart to have, but if you hear about holes in the heart, it's along that type of defect. And you can see the coloring here tells you about the posterior probability that the defect is significantly associated with, in quotes, the exposure. Red is bad, the bluish green color is good, okay? And a lot of these work in ways that we think might work. So that top row are having a relative who had a birth defect or had a heart problem, okay? And so you might imagine these are heart defects, and so having a relative who had a heart defect increases your odds of having a heart defect as well. The next line down, so some of these, I don't have a good pointer, but a couple things that are showing up in the pink shading here across the middle, these are type 1 in type 2 diabetes in the mother, okay, which is a strong risk factor for birth defects. The line below that is being obese. Again, not necessarily a great thing. Now, when you read these plots across, what we've done is we've started at 0, so that's the Dirichlet process, and then 3 different values of C, 40, 80, 120, and then infinity, which is forcing it to use our prior clustering. So you can see how the inferences might change for different values of the C parameter, or if you just use a Dirichlet process and ignore the prior information, or if you just use the prior information and not tried to do anything data adaptive with respect to the clustering. Most of this works in the direction that we would anticipate. A couple things are a little weird, and mostly the weird things have to do with medical conditions and the medication for those conditions, okay? And so we see, for example, fever's pretty bad. It's a little hard to pull out. You don't want to be hot when you're that's why they tell you not to go to the hot tub or something for long periods of time when you're pregnant. And so when we were looking at non-steroidal NSAIDs like Advil or ibuprofen, they originally looked weird, but once we isolated them from fever, they don't necessarily look too good. So, that's what we see for these defects. So just an example of the types of inferences we might make after the fact. We don't have, interestingly, the study is one of these large consortia, and we don't have individual odds ratios and confidence or credible intervals here for you to look at. One reason for that is that the way the study has worked is that people will each sign up to analyze one defect at a time and one exposure at the time. And so there are all these papers out there that are a little bit all over the map because I've picked my outcome and I've picked my confounders and I've done, basically my research all on my own. And somebody else might be somebody might look at type 1 diabetes, but somebody else might look at type 2 diabetes and they have slightly different models. And so trying to make everybody happy was really hard in terms of what control variables we had in the models. And for some exposures, people would feel very strongly that you need to control for X, and for others, they felt like you shouldn't control for X. And so we just went with red and green dots so that somebody doesn't look at our paper and decide somebody else's work is completely wrong, when maybe we just have a different set of confounders in the analysis. So that's sort of an interesting area to think about moving forward is how to address the confounding for causal inference. And that leads into some of the future directions that we're interested in. One is how we do variable selection within a cluster, how we incorporate prior information favoring a relationship between certain outcomes and exposures. So for example, if I did this analysis and I had gastroschisis as one of my defects, and I did not find that young, skinny women are at higher risk, I would not trust my results, And so how do I build in strong prior information if I'd like to? Methodologically, it'd be really interesting to think about how you build prediction rules for new observations or new clusters. And also, we may not have as much information on a clustering structure. We might just have partial information. So one reason we started with heart defects is that there had been a lot of work done on how to mechanistically classify heart defects. But once we move into limb defects, or once we move into clefts, it's sort of the Wild West. And people will do clustering based on where the defect is. So, is it a cleft lip, a cleft palate? It's an orofacial defect. But they haven't done as much work looking at embryology. For example, orofacial clefts, some types of them are more closely related to certain heart defects than they are to other clefts based on how the stem cells migrate in the embryo. And so that information is not as solid, and how we include sort of partial information where I can say maybe something about clefts and hearts, but I really don't know anything about clefts and anything else. How I build that in is something that's interesting to think about. And also, if we just want to make some specification about what the number of clusters should be, or about how large I would like them to be is another thing to do. So we have a paper in draft form. We're hoping to submit at school soon, so that Sally can get out of school and onto a postdoc. And so we'll put it on archive pretty soon. Just a bunch of references here, and I want to be sure that we thank our funders, which include the U.S. Centers for Disease Control and Prevention, as well as the National Institute of Environmental Health Sciences, which has been really generous in funding statistical and methodological research over the past several years. So with that, we'll take questions. Any questions, comments? Yeah, Peter.
I mean, I really like data, but maybe it's a good example for the alternative way of seeing the whole thing is to talk about utility and loss. Because like you started out by telling us your epidemiologists, they like certain partitions seem more plausible than others. It gives you actually more flexibility. For example, if your collaborators were to say we don't... Sorry, would you mind just summarizing? I think it's a good example for potentially using utility in order to express those preferences. Yeah. For example, if you wanted to say that you want to have only, you prefer to have 4 clusters, it's something very difficult to express with your centering, right? You would have to think about, how you specify a different type of distance metric, for example, to do. Like there wouldn't be a C0, right? You wouldn't have a reference C0. And although it's very easy to say about
times the distance between them. E to the minus psi of the distance between C and the number of clusters in C and the number of clusters in C0.
Good point. So you only use the
You'd have to redefine it, yeah.
Other stupid question. Did you ever tell us how you actually selected the partition that you showed us?
Oh, the one here.
Or any of the partitions that you showed us, because that's kind of a non-trivial matter where you need kind of the same considerations.
Yeah, that's something that I'm looking at David because it's something that we're still not exactly happy with, and and the problems. So what I showed you here was a sensitivity analysis, where we looked at 3 different values. But what you can do is you can calculate, the range, the maximum, and the minimum distance. And so we're using a decision rule like 90% of the time a randomly generated cluster and the prior is within a certain distance from our pre-specified clustering.
I didn't mean anything so complicated, just like you have model-based partitions, so the outcome of your inference is actually a posterior distribution on the random partition, but you selected one to put on the slides, which is not obvious how to do it. I mean, everyone has their favorite method. Which one was yours?
We were using the weight Germani.
High tech.
Can you just say that, like repeat it? Just.
The answer was weight and Germani.
Yeah.
Okay. Any other questions or comments?
Thank you very much for a really interesting presentation. I just would like to make a comment on how to choose the precision parameter in the Dirichlet process prior, because we kind of recently investigated relationships between sparse finite mixtures where you use a finite mixture, which is flexible enough that you are able to learn the number of clusters and Dirichlet process priors. And what we found there for smaller data sets, and you mentioned like 300 cases, is that it is more important how you select a prior on the precision parameter rather than whether you actually use a sparse finite mixture or infinite mixture. So it might well be, I don't know what the prior has been in the Dirichlet process, and something that I did not understand whether this alpha also pops up in the cases where you have the psi. But what we found is that the prior on these parameters, which very often is like a standard prior, can be extremely influential and influence the posterior distribution of the number of clusters in a way that you get a small number of clusters even if you use a Dirichlet process prior.
Yeah. Thanks. Yeah, it's tricky. In other settings, we have a lot of trouble actually picking that parameter to get a reasonable number of clusters. Yeah.
Any other comments?
You look like you want to say something. Okay. You have a lot of complaints?
Hi, how are you? Thanks for the presentation. I have a question regarding C0. So your prior needs to specify a partition C0. What if you have more than one possible partition and you want to, I don't know, average some prior information coming from different opinions, for example?
Yeah, I haven't thought about how to incorporate like a mixture of experts type approach here. That would be interesting in this setting because there are multiple partitions, and depending on what type of background the person's coming, you know, like the embryologist might have a slightly different view from the epidemiologist, who may be a little more informed by common risk factors across defects in different families, and they might be just purely on embryological development, but that's a really interesting
concept. You can do it automatically, but it's a problem of choosing the size, because then you can expand out
what the distance would look like.
You can expand out the psi d of C0, and so if you had multiple C0s, you could just write out an additive function, and so you could have psi1 d C01 plus psi2 d C02, and then you could even do that in a hierarchical way if it was coarse defined. But then it would be more of a more difficult prior elicitation problem is the main question. And the data don't give you that much information, which is one of the whole points of trying to put in more prior information. And so if you let it be too free about choosing the psi, then it almost eliminates the point. So.
Yeah, we're struggling enough with the psi for one. I'm not sure how ready I would be to try it for multiple.
Maybe you could just run multiple models and see what difference it makes if you start with the different
price. You put one psi and put both average.
Yeah, you could average.
Psi times d this.
Yeah, what would the distance mean in different, it's interesting, yeah.
In your slide with the red dots and the green dots, I noticed that there was a lot of correlation between the coefficients in the four.
Yeah.
And is that a part of your model, or did that just come out of the data?
It's mostly in these cases. So if you're looking horizontally, you know, they're correlated because there's just different values of the C parameter. And so here we're just looking from Dirichlet process to a more and more strong focus on the prior classification. So that's what's causing this. But then there's also quite a lot of correlation if you're looking vertically in terms of how things might act, and also in terms of sort of multicollinearity. So you wouldn't be very likely, for example, to have type 1 and type 2 diabetes, though that is possible. But they act in very similar ways in terms of pregnancy risk, at least for these defects. However, a lot of these are, you know, having a fever and taking medicine designed to get your fever down, okay? And so for those, what we've tried to do in the coding is to code things so that you're taking NSAIDs without a fever, NSAIDs with a fever, and so forth, to try to disentangle the medications and the indication for which the medications are taken.
I meant more about correlation between the four tables.
Oh, between the four tables, yeah. So that is coming from the grouping. So we can look at these four.
Are these in the same partition?
Yeah, so let's look here. So for the Dirichlet process, we've got, so let's go back, truncus, PAPVR, pulmonary atresia. So PAPVR is not in the same, so they're not exactly in the same. So PAPVR is red, okay? So that's one of the ones we're pulling out. We have atrioventricular septal defect, which was put in a group all by itself. So people disagree about that one in terms of which group to put it in. Okay, so the yellow one, the red one, the pulmonary atresia is the blue one, and then what's the other one we had? Truncus arteriosus. I don't know why I'm not seeing truncus on here, but it could just be my bad eyes. So I'm not seeing it on this one. But so in this case, they're in the same, so we have 1, 2, 3, all in the big block two down here, and Papver's up there. But you can see that one's a really interesting one. It's the fourth one down in red. It's really hard actually to cluster that one. You can see the darker gray. So it really was a little unsure where to put that one. This is in the Dirichlet process. The plots I was showing you are from the centered partition process. So you can see now that we have, things, some of which are in the same group. So the yellow and the red up at the very top, those two were stuck in the same group, but they weren't all. So
one thing I was wondering about as well is that in your model, something either is in the same partition or not, and then they share the same parameters or not in that particular.
Oh, pardon?
And then, so what I was wondering about is if there's room for a more hierarchical interpretation of the partitions, where you could have some big partitions for hard defects, which have some coefficients associated with them, and then that gets subdivided more with tighter priors, with smaller partitions. Is that something you're looking at as well, to have a more hierarchical kind of tree of partitions?
So that's actually how the defects are classified. So we sort of picked a middle of the range classification in terms of a tree. And we would definitely do that when we move to incorporate defects from other parts of the body. But because some of those are very strongly hierarchical. But right now we haven't incorporated any of that. So we just have sort of the 6 groupings, but we haven't included any of that structure. Yeah. But that would be extremely interesting. We do get into some very small sample sizes if we start.
You got tighter priors.
Yeah. That's a good idea.
Okay, well, we need to bring the discussion to a close, but let's thank Amy again for her presentation.
Thank you.